So to see these effects in practice, let's consider an example study from literature. This corresponds to a 14-kilometer urban fiber link in Saarbrücken, Germany, and it's connecting Saarland University and the University of Applied Sciences. The link is partially underground and partially aerial. Uh, this particular work characterized time-dependent drifts in the fiber links and was intended for both classical and quantum channels in their experiments, which helps us understand how environmental disturbances affect these different degrees of freedom and loss in the photon, etc. And let's start by taking a look at their experimental setup. Here, one of the photon from an entangled pair that is generated at the first node is detected locally, while the other is converted to the telecom band and it is sent through the urban fiber link. For many of the classical characterization experiments, the signal is looped back and detected at the first node, and in some cases, after altering the signal in specific ways at the second node, it is looped back. So the drift in the link and the fiber's influence on photon timing, polarization, and other properties is studied in detail. During quantum experiments, detected signal at the second node is encoded onto an optical pulse and sent back to the first node so that time tagging can be performed in the same node that generated the source. Both the photons are tagged at the same node. Let's first start by understanding what were the observations with regards to timing fluctuations. For this, interferometric transmission time measurements were performed, where the classical signal was sent through the fiber. Its frequency was slightly shifted at the end node, and it was looped back and was interfered with the reference signal so that that helped detect the arrival time differences over multiple days. The results that we see here, they show a strong correlation between temperature fluctuations and the photon arrival times. And this basically originates from temperature dependence of the fiber's refractive index, which in turn changes the effective speed of light in fiber, and this causes the observed drift in arrival times or delay. And next, we can consider the polarization measurements that was conducted. In this particular case, two fixed reference polarizations were sent in as inputs, and they were altered periodically by measuring the output polarizations, the rotation matrix that is introduced by the fiber, and corresponding parameters that describe this rotation matrix known as Stokes parameters. Those are plotted, and in fact, this measurement is done for a couple of days, but we see here as a function of hour of the day. So from these results, we see that the fluctuations are way stronger during daytime, and this is likely due to increased human activity and potentially some temperature fluctuations as well, while the nighttime fluctuations are much lower. So, for example, this here illustrates the need for faster compensation during daytime operation in real-world deployed networks. And let's also move and talk about loss, specifically polarization-dependent loss, or what we call PDL here. In fiber, two orthogonal polarizations, say typically horizontal and vertical, can experience different losses as they propagate. And this difference in loss reduces the fidelity of the quantum state received at the end node. And for this link that was studied, the polarization dependent loss was measured over time, and the average value was used to estimate the expected fidelity of the transmitted states. And it was found to be around 99% and greater, which is excellent for QKD application. And at this level, the effect of polarization dependent loss can essentially be neglected. The extent of the effect is very link specific, and it also depends on link distance. So here we see an example where characterization does play a crucial role in determining which metrics have stronger effect on the link and helps inform what sort of compensation techniques is necessary, if it is necessary at all.